In this example, we are asked to graph the set of parametric equations by making a table of values. This particular situation will have a special type of graph that is going to be known as an asteroid. X is defined here to be equal to 2 times cosine to the third power of t, and y is equal to 2 times sine to the third power of t. We have that t is restricted to be between 0 and 2 pi, and we are also recommended, or given a hint, to use increments of pi over 4. That means that we are likely going to be plugging in values, at least, of 0, pi over 4, pi over 2, 3 pi over 4 pi, and so on and so forth. We will get our values of x and y back in return. The reason for this hint is because if we do not do that and use those increments, we may have a misconception as to what the shape of this graph actually is. I would say that if you actually just use 0, pi halves, pi, and the typical phi values there, you may think that this graph is actually a circle, but this will help us figure out what it actually looks like. Now, in order to evaluate these, a few of these we can do without a calculator, and in fact, we should be able to do all of these without a calculator. But I am going to use a calculator for some of these in order to approximate them to get a little bit of a better decimal. For 0, though, we should not need a calculator for. Recall that when you have an exponent on a function like this would be read as 2 times cosine of t, and that cosine of t is taken to the third power. So if I plug in 0 there for t, I'm really doing cosine of 0, taking that to the third power, and then multiplying it by 2. With that in mind, same thing with sine would be 2 sine of t to the third power. With that in mind, for cosine, cosine of 0 is 1. 1 to the third power is still 1, and multiply that by 2, and you get 2. Whereas for the second one, sine of 0 is 0. 0 to the third power is still 0, and 0 times 2 is still also 0. Now, if I plug in pi over 4, we can also do that by hand. Cosine of pi over 4 would be square root of 2 over 2. To the third power, that would be 2 to the 3 halves power divided by 8. If you multiply that by 2, you'll get 2 to the 3 halves divided by 4. Overall, what that means is that you're going to get 1 divided by the square root of 2, or the square root of 2 divided by 2. But we can use a calculator to approximate that and get the same thing, and I'll do that in this particular case. So if I do 2 times cosine of pi over 4, which I'm going to make sure real quick that I'm in radian mode, since we are plugging in a radian measure in for cosine here. 2 times cosine of pi over 4, and that is taken overall to the third power. Careful of your parentheses here. This gives us the square root of 2 over 2, which is 0.707. And since this is cosine and sine, and both sine and cosine will give you the same overall input, we're going to get the same thing for sine as well. When I plug in pi over 2, cosine of pi over 2 is 0, so that overall is going to give me 0 here. Whereas for sine, sine of pi over 2 is positive 1. 1 to the third power is 1 times 2 gives us 2. So we're probably going to see this kind of cycle. When I plug in 3 pi over 4 into this function instead, so 2 times cosine of 3 pi over 4, we're not going to see too much of a change, because the only thing that's really going to change about this is that the inside is going to first come out negative. When you take a negative to a third power, it will still remain negative. Meaning, I expect to get the same answer as before, but negative. So negative 0.707, Whereas sine of 3 pi over 4 is positive still, so that's going to still give me 0.707. For pi, cosine of pi is -1. -1 to the third power is -1. And -1 times 2 is -2. And then for sine of pi is just 0, so that whole thing will equal 0. So let's see about plotting these points. There's still more to go since we need to go up to 2 pi, but we can probably see what's going to happen with this. If I plug in the first point that we got, 2, 0, that's right over here. The second point, 0.7 and 0.7, so that would be around here-ish. And the third point of 0 and 2. It's first, second, third point would be up here. So it seems like we're curving up to that peak on the y-axis. I say peak on the y-axis because if we look at the fourth point, -0.7 and 0.7, that'll put us at the same distance from the origin. It's just in quadrant 2 now. That's our fourth point. And then -2 and 0 puts us back on the x-axis for our fifth point. If I connect these together, this is curving up to the tip on the y-axis, and then it's going to curve back down towards these points. If you would like to always test other points in between, like 5 pi over 6 or 2 pi over 3 or anything, you are always welcome to do so. If I were to continue through this pattern, though, with 5 pi over 4, 3 pi over 2, and so on, all I'm going to see are the same values in this case, just with different positives and negatives. If I do 5 pi over 4, both of these are going to be -0.707. If I plug in 3 pi over 2, it'll be the same as pi over 2, but with a negative y. And so that's going to curve in here for the 6th point, and then to the 7th point at the bottom. And from here, you could probably anticipate what's going to happen. The last 2 points that you would plug in would be for 7 pi over 4, and then finally 2 pi. For 7 pi over 4, x will be a positive 0.707, y will end up being negative. And then for 2 pi, we'll get the same as our initial point. So 8 would be here, and the 9th point would be right back where we started. This would be our image of our asteroid. Last thing I do need to do, though, to make sure that this graph is correct, is to include the orientation from the first point and the track that we follow. So our first point was over here on the x-axis, and then we followed this way all the way through. You typically don't need to have arrows between every 2 points that you have, but it is a good method to have, or it's a good thing to fall back on to make sure that it's clear what the orientation of your curve is.